Paralysis due to spinal cord injury limits mobility and results in degenerative changes to almost every organ. Consequently, paralysis threatens overall health and compromises a productive lifestyle. Our goal is to develop a muscles first cyber-physical walking system, or CPWS, that integrates three concepts. First, a person with a spinal cord injury with neuromuscular implants to stimulate their muscles. Second, an exoskeleton with DC motors. And third, computational algorithms that continuously and automatically learn to improve standing and walking stability. The CPWS is equipped with electric motors at the hip, knee, and ankle. Conventional orthotics are used for the trunk and shank, while each joint features its own separate power module with a brushless DC motor, electromagnetic solenoid brake, and harmonic drive transmission. The power units are connected by aluminum tubing with customizable limb length, and pyramid adapters allow for 15 degrees of passive fitment adjustment in the sagittal and coronal planes. In the muscles first approach, the user's muscles provide the majority of the torque required for walking, while the DC motors provide joint power assistance as needed. Recruiting the muscles helps maintain musculature, counteract muscle atrophy, and improve circulation. Part of the assessment of the CPWS is to determine the rate of metabolic consumption during usage of the device. Due to its unique back-drivable design, the SCI exoskeleton pilot can move the system using neural stimulation of the lower limb muscles. To assess metabolic consumption, able-bodied pilots were instructed to move the system under their own power while wearing the K5 metabolic system. Ideally, the CPWS should be invisible to the user, so any increases in the metabolic consumption indicate that aspects of the system impede the user's generated motion. We've found that the amount of viscous damping at the joints has a significant effect on metabolic consumption. We've also tested the CPWS with a participant with a spinal cord injury in a walking experiment. Shown here, the muscles are activated via neural stimulation in a typical walking pattern, while the electric motors provide ballistic assistance with timed bursts at various phases of the gait cycle to help complete the motion. The controller also compensated for friction to help make the device feel more invisible to the user. Every exoskeleton pilot is different, with each pilot differing in weight and limb length. Each SCI pilot may have different muscles available to be recruited, with varying levels of atrophy. The guiding question is, can an exoskeleton learn to adapt to the SCI pilot's unique characteristics and muscular ability? We have implemented a biologically inspired terminal iterative learning controller that learns how to step better the longer that it walks, and fluidly distributes the control effort between the neurally stimulated muscles and the exoskeleton motors. The learning algorithm exemplifies the muscle-first philosophy by maximizing recruitment of the lower limb muscles to accomplish stepping, while the motors apply a biologically inspired bursting paradigm to ensure the limb is in the correct configuration for weight acceptance. Additionally, we have been evaluating perturbation responses with able-bodied study participants. The actuated ankle joints are controlled by a simple PD controller tuned to maintain an erect standing position. In these destabilizing experiments, the participant is pulled in the forward direction by a linear actuator, while the PD controller helps counteract the perturbation. We prescribed 3 separate perturbations with magnitudes between 3 and 5% body weight. The study participant does not know the magnitude or time of the next perturbation. In these destabilizing experiments, the participant voluntarily moved objects between 2 positions on a table in front of them, while the controller assisted in returning the user upright. Taking advantage of the modular nature of the CPWS system, we recently adapted it for unilateral assistance for stroke survivors. This version incorporates an exoskeletal knee and surface stimulation. Stimulation is applied to generate ankle dorsiflexion and plantar flexion, as well as knee extension and hip flexion, while the motor acting at the knee ensures flexion for toe clearance in swing and knee stability in stance. In this way, the stimulation enhances walking speed and the exoskeletal knee ensures safety. We recently recruited a person who had a stroke as the first study participant, and we're developing the control algorithm to coordinate assistance based on sensors mounted on the powered orthosis. We will then evaluate the impact on walking ability.